Hello everyone, I'm Xiaochang Chen. Today I will walk you through our work on explainable AI and fairness analysis in loan default prediction. Our goal was to train a model to predict whether a borrower will default on a loan, while ensuring transparency, interpretability, and fairness and in decision-making process. We followed a structured approach covering data pre-processing, model selection, feature importance analysis, explainability methods, and fairness evaluation. So let's dive into the details now. In first part, data preprocessing and model training, we worked with a data set containing various loan-related features, such as loan amount, earliest records credit history, loan interest rate, and job title, and more. And the data was cleaned, normalized, and split into 80% training and 20% testing using PyCarrot. We automated the machine learning pipeline, including data preprocessing, feature selection, and model training. We tested multiple classification models, and after comparing performance metrics, the best model was linear discriminant analysis, which is LDA. Let me show you. Yeah, here. And to enhance performance, hyperparameter tuning was performed using PyCarrot's ultimate tuning framework, which optimizes model parameters systematically. The learning curve analysis from PyCarrot revealed that, uh, yeah, revealed that the well that while the model generates the well, some overfitting exists, suggesting room for improvement in feature selections or regularization. A learning curve analysis showed that while our model generates the well, overfitting exists, indicating potential improvements through regularization or additional feature engineering. In next part, feature importance and model interpretability. We will show you that how we make sure our model isn't just a black box. We used a few different explanative technicals to break down why it's making certain prediction. Number one, we use like permutation importance. Yes, here. To make sure our model isn't just a black box. So what features really matters? Turns out like loan amount and earliest credit history was the two biggest drivers of default risk. Surprisingly, things like interest rate or long term, which we'd expect to play a big role, barely matters. And then we use shape, seeing how features push predictions. Looking at our shape summary plots, we saw that highest is loan amounts. It's always pushed the prediction toward default. And more recent credit histories, meaning the person hasn't had credit for long, also increase default rate. Other features like grade and total accounts had some influence, but they weren't nearly as strong. Then we use Lime. Um, yes. Breaking down a single prediction, we pick one borrower and ran Lime to see why they were classified as high risk. They had a loan over $21,000 in higher installment payments, a lower employment title score, and a moderate credit rate. Lam showed that loan amount and employment title were the biggest factor driving the default prediction. Number four, decision tree surrogates model. Uh, it's here. Let me show you. So it's mimicking our model's decision. To simplify things over further, we're training a decision tree surrogate model to see how our main model is making decision. The key takeaway is that if your loan amount is below 19 and 18 827, you are probably safe. And if it's above 20,000, your risk shoots up. And this confirms what we saw earlier. Loan amounts dominates everything else in this model. So overall, this explainability tools help us understand exactly what's driving default predictions instead of just blindly trust the model. In the next part about fairness and the bias analysis, um, here. So now even if the model is accurate, that doesn't mean it's fair. So we dug into the number to see if certain groups were being treated unfairly. Number one, approved rates. So do some people get loan more easily than others? When we look at the loan approved by credit grades, we saw something troubling. People with the highest grades, which is 6 to 7, had a 40% plus approved rates. Those with the lowest grades, which is 1 to 2, less than 10%. And this suggests our model might be unfairly rejecting lower credit borrowers, even if they could still be financially responsible. Number two, about accuracy, this partial, these parties, sorry. Does the model perform equal well for everyone? When we checked accuracy across different demographic groups, we found some big differences. Some groups had super higher accuracy, which is nearly 80, 90 hundreds. Other was struggling with less than 40% accuracy. This means the model is way more reliable for some people than others, which could lead to unfair leading decisions. Number three, about demographic parity. Are loans distributed fairly? We ran demographic parity matrix to check if one group was getting more loans than other. The result shows clear disparity. Certain groups consistently got fewer approves. If we were like here, if we were deploying this in a real bank, this could create serious ethical and legal issues. Number four, anchor explanation. Does the model follow? We also use anchors. It's a method to find patterns in higher risk borrower. The model consistently flagged people as a higher risk if they had let me show you. I'm sorry, it's here. Loan amount over than 80 hundred, and employment title, which is smaller than 12, and early credit history, which is smaller than 176. This means the model isn't considering a well-rounded financial pictures. It's really relying heavily on just a few rules. Our model isn't just predicting defaults, it's also reflecting existing bias in the leading system. If we deployed it as is, it would likely reinforce financial inequalities instead of fixing them. And about model performance and explanation consistency. So here we're evaluating our model's performance here. So the EUC indicate moderate predictive power, but there's room for improvement, and accuracy is acceptable, but precision and recall highlights a need for better default detection, but recall is really better. And F1 score reflects imbalanced performance, suggests a need for better feature engineering or model refinements. Actually, I did some other models like XGB Boost, the Light GBM. They did very well, but because of the time limitation, I just used the startup book. And to assess the stability of explanation, we compared explanation consistency scores. Yes, here. The Jaccard similarity is 0.25 and causing similarity is 0.9, nearly 1, indicate that explanation vary across similar samples. Overall consistent score is 0.58, suggests that well explanations are somewhat reliable. Further refinement is necessary. To sum up, we successfully built an interpret loan default prediction model, applying XAI technicals to explain decision and fairness matrix to assess bias. However, there are some key areas for improvement. Number one, enhancing model accuracy, possibly by incorporating additional features or using more sophisticated algorithms. Number two, mitigating bias. By rebalancing the dataset or applying fairness constraint during training. Number three, improving explanation stability, ensuring that model explanations are consistent and trustworthy across different predictions. As AI systems play a growing role in financial decision making, it's crucial to prioritize fairness, transparency, and accountability. With further refinement, we can develop models that are not only accurate, but also ethical and fair. Thank you, and I'm happy to take any questions.